Good morning. I'm Dhiraj Gupta, consultant cardiologist, electrophysiologist at Liverpool Heart and Chest Hospital in the UK. It gives me great pleasure to share my initial thoughts on the IntellaNav STABLEPOINT catheter. I would like to thank Boston Scientific for giving me the opportunity to use this catheter as soon as it has been launched in the UK, as soon as it received the EU approval. The title of my talk is How has the use of this catheter enhanced my AF ablation practice? Now, to put this in context, I have been performing over 200 focal RF AF ablation cases per year for over 10 years. So that's over 2,000 cases. So for any new technology to significantly enhance my ablation practice, we'll have to meet a fairly high bar. These are my conflicts of interest. Of note, I am the chief investigator of a research study that is funded by Boston Scientific. Also, I have received speaker fees from Boston Scientific, including for this talk. Let me start by reminding you of the biophysics of radiofrequency ablation. Now, the three most important determinants of an RF ablation lesion size are power, ablation time, and contact force. Of these, power is the most important. The ablation time tends to be less important the longer the lesion goes on for. Now, all of these three are modifiable factors, and the more you increase either or all of them, more is the electrical current that flows through the tissue, and more is the heating that results, and obviously the heating-induced necrosis and lesion formation. Now, what is very important is the underlying impedance of the circuit. And this often is not within the control of the operator, because Ohm's law states that the circuit impedance is inversely proportional to the electrical current that's flowing through the circuit. So if you've got a lower impedance, you'll have higher energy transfer. And that's why some people try to reduce the circuit impedance by putting an extra reference patch, for example. Now, it's also important to see the impedance of the circuit at baseline, but equally, it's important to be able to track the changes in the impedance during RF delivery, because as the tissue gets heated, the impedance in the circuit decreases, and you often have the impedance value decreasing over time. In fact, there have been many studies over the last 10, 15, 20 years which have shown that the quality of the RF lesion and the efficacy of the RF lesion depends on the amount of drop in the generator impedance. Now, a couple of years ago, we were invited by Jack EP to share our secret sauce, as it were, of a high-quality RF AF ablation. And this essentially is my recipe. The goal of RF AF ablation is very simple: to create contiguous, durable lesions safely. And the way we do it in our lab is use general anesthesia and steerable sheath because it maximizes catheter stability. We perform point-by-point ablation using software that allows objective lesion tagging. We also use a catheter that allows us to see the contact force being applied, because once you know what contact force you're using, the other two variables, that is power and time, become much more easier to control. And then, of course, you can increase the power, and correspondingly, you'll have a decrease in ablation time, and that enhances safety of the ablation. And there's lots of data of high power, short duration ablation being safer than the traditional ablation, especially on the posterior wall. We also use software which allows us to track the distances between adjacent RF lesions, and we try to keep that less than 6 millimeters so as to ensure contiguity of the lesion set. And then finally, it's desirable to be able to track the impedance drop for each lesion, so you can see what is happening in response to the ablation that you're delivering. So this is the other end of the equation, as it were. So you can control contact force, power, and time, but you want to know what effect all of that's having on the actual tissue. And the impedance drop will allow you to monitor that. Obviously, back in 2018, the only way we could do that was through tracking the global impedance or the generator impedance. Now, obviously, generator impedance had some disadvantages in that it was, because it was over such a large circuit, it was dependent upon lots of other factors, such as where the reference patch was placed, for example. Was it on the thigh or was it on the back? And also, it depended upon impedance of the entire thoracic wall. Now, obviously, that could lead to errors. What changed in 2018 was the advent of this catheter, IntellaNav MiFi OI catheter, which allowed us for the first time to measure local impedance across the catheter tip and the tissue interface. And this was it was novel at that time, called Directsense Technology. And this paper by Claire Martin and co-authors from Bordeaux showed that the absolute drop in the local impedance value correlated highly with success or otherwise of a lesion, and also the percentage drop in the local impedance correlated with the successful lesion as well. Now, important to bear in mind that this catheter had 3 MiFi electrodes, and the way the technology worked was that a non-stimulatory electrical current was passed between the distal electrode and the R1 electrode, and then the voltage was measured between these MiFi electrodes and the proximal electrode, and that is what gave you the direct sense impedance value. But up until recently, one had to choose between catheters which either give you contact force data, such as the ones with the Carter platform or the abla platform, or catheters that gave you local impedance data or direct sense impedance data, such as the one with the Boston Scientific or Rhythmia platform. However, with the advent of the STABLEPOINT catheter, you don't have to choose between these two anymore. So you can get both the information in one catheter itself. And how important is that to give you a quality RF PVI lesion set? So we'll have a look at that. So this is a STABLEPOINT catheter. That's how it looks like essentially. Right? It's got a spring coil mechanism which allows you to give an idea about the contact force. Essentially, when the spring deformation is then translated into 3 inductive sensors, which are placed coaxially around the catheter shaft. It's slightly different from the smart touch catheter that you may be used to with the Cardiologist platform, which are magnetic sensors. But essentially, the concept is the same. So you get an idea of the numerical value of the contact force, but also the direction. And of course, you also have the direct sense capability of this catheter, as with the IntellaNav MiFi. Now, a point worthy of mention is that the way the direct sense technology works with this catheter is different from the way it worked with the MiFi catheter. Because there are no MiFi electrodes in this catheter, the voltage is measured between the entire distal tip as well as the R1 electrode. So unlike in MiFi, where it is measured from the MiFi electrodes and the R1, here the entire distal tip is used to measure the voltage drop. And what that means is that the baseline local sense impedance value with this catheter is about 50% higher than what you get typically with the MiFi electrode. So on a practical level, what this means is that your blood pool values with the STABLEPOINT catheter are, as I said, about 50% higher, something like 120 to 130 ohms. And then depending upon the quality of the contact, that value increases. So it can range for anything from about sort of 170, 180 to 200 ohms, depending on how good the contact force is. And you can actually see it in the lab. As you increase the contact force, the direct sense impedance value keeps on increasing. Also, the range of drop during radio frequency application changes. I always like to use the percentage drop in impedance as a quality of the as an indicator of the quality of the lesion. So usually about 15 to 20% drop will tell you that you've got a very good lesion. And obviously, once the baseline impedance is higher, that the absolute value of impedance drop that you expect to see is also going to be higher. So I'm just going to use a recent case example to illustrate the different features of this technology. This is a chap who we took to the lab on the 27th of July. He had quite a complex history. He had mitral valve repair, left atrial appendage clipped surgically, done in August of 2018. And since then, he was in recurrent persistent AF. In hindsight, he may well have be better off having had a surgical AF ablation at the time of the surgery, but that didn't happen. Anyway, he kept on being admitted to hospital with recurrent persistent AF, which was resistant to electrical cardioversion. He had good LV function, moderate left atrial enlargement, and he was referred to us for AF ablation. So my workflow is quite simple, really, and it's consistent across all cases. And consistent across platforms as well. So the first step is to create a baseline voltage map of the left atrium. So if the patient is in atrial fibrillation, I would cardiovert the patient, and during constant coronary sinus spacing, I would create a voltage map of the left atrium. Obviously, with the Boston Scientific technology, you would use the arrhythmia voltage mapping using the Orion catheter. Now, there are lots of advantages of creating voltage maps before you start off ablation, because you can get to know what the anatomy is like. You can get to see how muscular the pulmonary vein antra are. So it allows you to determine how proximal you need to create your Waka lesion sets. It also gives you an idea about atrial scarring overall in the chamber. Now, I don't necessarily chase the atrial scar in terms of ablating it to improve my outcome, but it gives me a very good idea about the likely prognosis in terms of AF or sinus rhythm maintenance after ablation. So if somebody has lots and lots of scarring, you can tell the patient afterwards to be realistic in his or her expectations of maintaining sinus rhythm. Once I've created the baseline voltage map, I would then advance the ablation catheter into the left atrium, obviously stable point catheter in this case, and then spend a couple of minutes warming up the catheter, zeroing the contact force, and also determining what the blood pool Directsense impedance value is. Once I've done that, then I create road maps around both the Waka circles. So I use the contact force sensing catheter, the stable point catheter, and then go all around each Waka and give myself location-only points at areas where I've got good contact force, and more importantly, I've got a stable position. So I know that I'll be able to deliver a good quality RF region there, and I'll show you a couple of images of this. Once I've done that, I then get on with the actual RF application, delivering point-by-point contiguous RF application around both Wakas. And then finally, I use the Orion catheter to create a arrhythmia map. Look for gaps. If there are any gaps, you can obviously pick them off. And otherwise, finally, you want to validate pulmonary vein isolation by creating voltage maps as well. Briefly, my AutoTag display settings follow the rule of 3. So I use a tag size of 3 millimeters because, as you know, a tag size of 3 millimeters means a circumference of, or sort of diameter of 6 millimeters. And obviously, most lesions that you create with these settings are going to be about 6 millimeter wide. So if you use a tag size of 3 millimeters, you can, by and large, ensure yourself a contiguity between lesions. And obviously, if there are any obvious gaps between adjacent tags, then you know that you've left a gap there. So tag size of 3 millimeters, using stability of 3 millimeter movement within 3 seconds. So I don't have a very long period before the AutoTag appears, because I want to be able to see even very brief, even tags where I've delivered RF very briefly. And this is particularly important because I use a power of 50 volts with a target contact force of 10 to 40 grams. What that means is that you often have fairly substantial lesions quite quickly, especially on the posterior wall. So you want to make sure that your AutoTag settings are such that you see the lesion earlier rather than waiting for 10 seconds, as some people do. What I actually use to display on the AutoTag is the Directsense impedance drop, and I'll show you that you can choose between many different factors. I prefer this one because, again, this tells me what is the impact of what I'm doing on the tissue. So I want to see that. I don't want to see contact force or time, because that's I can see on the generator. I want to see how the tissue is responding to my delivering the lesion, delivering the ablation energy. And then that I can only see with the impedance drop. Typically, the duration of RF lesions on the posterior wall are a maximum of 10 seconds. or a direct sense impedance drop of 15 ohms, whichever comes earlier. And on the anterior wall, maximum 20 seconds, or generator impedance drop of 25 ohms, whichever comes earlier. Now, what this means is that your individual RF applications are often quite short. And that's what I've noticed since I've started using 50 volts everywhere for my carto cases a couple of years ago, that you can actually create very good quality lesions quickly, and you don't have to ablate at individual sites for a long time. So 10 seconds max on the back wall, and usually 20 seconds max on the front wall, provided you've got a decent contact and good contact force, you will see that you will get a very good direct sense impedance drop within this period, and that often is enough. So this is step one. You create a voltage map with rhythmia mapping. In this case, you can see the voltages are reasonably well preserved, both anteriorly as well as posteriorly. And once you do that, you just introduce the stable point catheter inside the left atrium. Of course, this patient, you can see there is the mitral valve repair ring, and obviously the left atrial appendage surgical clip as well, the atrial clip. This is the esophageal temperature sensor, which is close to the right side on the veins. This is the actual catheter advanced via a deflectable sheath, which in this case is a Gillis, but of course there's a whole variety of deflectable sheaths that you can use. And then you set up the stable point catheter. You use that by warming up the catheter in the blood pool. It takes a couple of minutes. And during that time, you can still move the catheter around, but obviously you can't deliver any radiofrequency ablation because the contact force will not be visible. So once you've warmed it up, you then zero the contact force, and then you're good to go. And this is what I mentioned about creating roadmaps around both workers. So if you can see these white blobs, so these white orbs are where I have put the put the catheter all around the worker on the right side, and then similarly on the left side. And what that means is that when I start delivering the radio frequency energy, all I'm doing is I'm going from one white blob to the other. So it sort of breaks the journey into little steps, as it were, and you can just keep on focusing, going from one to the other. And as you do, your physiologist can keep removing these white blobs, and so you know that you are making progress. And I find this very useful, not only when I'm doing the case, but also if I'm supervising a trainee doing a case, then there's a very clear roadmap for him or her to follow. Now, for those of you who are used to using the arrhythmia platform for ablation, you would be aware of the wealth of information that you can have on your screen. So you may well already be aware of the Directsense value widget, this one, which gives you an idea about what the Directsense impedance value is, both at baseline and obviously as it changes with ablation. You also would be aware of the Directsense impedance graph, so you can see it in the same information in a graphical fashion. Now, the widgets that are new with the stable point catheter are obviously the ones that display contact force information. So you've got this very important widget, which gives you a force value, but also importantly, a force angle. So it goes from 0 degrees to 90 degrees. So if you've got the force straight end on, then it's 0 degrees. But if you've got a force which tangentially, it'll be 90 degrees, and obviously everything in between. So what it doesn't tell you is the direction of the force, i.e. whether it's sort of left or right. But that you will often know from the catheter anyway, but it gives you the all important information about, is your force end on or is your force tangential? On the catheter tip, you've got this arc, which again you may be used to in the past. With the older catheter or MIFI catheter, you could only get the Directsense impedance value here. But of course, with this, you can get stable point or contact force information as well. And that's what I prefer. So it will give you, as I will show you in the next couple of screens, it will show you contact force data. The stability of the contact force data are in that arc live as you're moving the catheter around, which is very useful. So contact force widget, as I said, this is going to be your friend when you're using the catheter to deliver ablation. So if the force is applied perpendicular to the tissue straight ahead, so the widget was going to point towards 0 degrees. And when the force is applied parallel to the tissue or tangentially, it's going to be close to 90 degrees. And the maximum displayed force is 100 grams when it's perpendicular, or 50 grams when it is parallel to the tissue. And of course, you can get the same information in the form of a graph as well. I find it quite useful because I set myself some targets or limits as to what contact force I'm going to be using. So for in this case, it's between 5 and 20 grams. It will display as green. Up 50 grams or higher, it'll start flashing red. But anything between the upper limit of what you have set as your target and 50 grams, it will be yellow. So it's like a traffic light system. So essentially green when you are within your set range, yellow when you're above it, but not quite at the 50 gram mark. And obviously anything above 50 grams then starts flashing red. Now this is how the widget is in action. So have a look at this. So as I'm changing the direction of the angle, it's changing from 90 degrees to 0 degrees. And as I'm increasing the contact force, this value is changing. So my set value is between 10 to 40 grams. So as long as it's between 10 to 40 grams, this is green. And as I keep increasing the contact force, it becomes yellow, as you will see. And then finally, it becomes red. So here you are, white when it's not quite at the level, green when I'm now in my target range, yellow when I've gone above the target range, and then red when I have reached 50 threshold. And you can see it says high. The whole screen starts flashing red. So you obviously, it's a warning sign for you that your contact force is reaching the levels where it might lead to complications. So these are the AutoTag settings that you can choose. As I said, you can choose between time, the direct sense impedance drop, contact force, the radio frequency, the generator impedance drop, and the median power. And I always use the direct sense impedance drop. The reason being, everything else I can see from other sources anyway. I know what time I'm ablating for, what force I'm using. Obviously, with generator impedance drop, I'm getting, median power I'm controlling. Now, what I don't know and what I want to know is what effect I'm having on the tissue, and that I can only get by the impedance drop value. So I typically would put that at about 17 ohms for the posterior wall and about 22 or 25 ohms for the anterior wall. And I'll show you in the next one. So this is how the AutoTag works. So I'm going to turn the power on in a moment. There you are. So once it turns orange, the power is on. And the direct sense impedance value is decreasing. It's minus 16, 17, 18. Once it crosses the threshold of 22 ohms, which I've set in this case, the tag will turn red. There it goes. So it's more than 22 ohms, and it turned red. So you can see it. The contact force I've got is about 15 grams in a sort of perpendicular orientation, which is what I want, between 10 and 40 ohms perpendicular. And I've started burning at 50 watts. And then very soon, within a few seconds, I have reached my target impedance value. This, by the way, is on the right anterior carina. And then I find this distance indicator tool very handy. For those of you who are used to using Carto system, you would be familiar of this sort of IntellaNav distance measuring tool as well. It's very, very useful. One important difference with the Carto system, though, is that this distance indicator works not in terms of your last applied RF region, but the closest AutoTag in vicinity. So look at this here. For example, I started off from this particular burn. It was measuring off this AutoTag, but now it's measuring it off this AutoTag. And as I move the catheter further, it will then start working off this AutoTag. And I find that quite useful because that's all what you're really interested in is how close you are to a RF lesion that you've delivered in the immediate vicinity, not necessarily where you were delivered the last time around. So I find that quite useful. The step 4, the all-important step, is to create good quality contiguous lesions all around your wide Waka circumference. So this just gives you an idea of what we've been doing on the right side. So this is the right anterior. So I started off at, if you like, so 9 o'clock on the clock face, go down to 6, then work my way on the posterior wall, and I'm coming back towards the anterior carina. As you can see, all the ablation lesions on the anterior wall are bright red, which means that I have been able to achieve a direct sense impedance of at least 22 ohms. On the posterior wall, they are less impressive. So anything between sort of 17 to 22 ohms. And here where I found the esophagus, They were less than 17 ohms, but that's fine. Safety is the most important thing. You'll remember from the initial image I showed you of the X-ray that the esophagus lay very much on the right side. And so when we started it and getting esophageal temperature rise, I stopped. So we had impedance drop of only about 10 to 15 ohms here, but that is fine. We accepted that. Similarly, on the left side as well, we just go around. What's very important here is the use of the force direction. Now, if you're used to using Carto, you know that it's got a force directional vector, which is very handy, especially on while ablating on the appendage ridge, because there you are, just before you fall off from the vein into the appendage, you get that arrow which points you anteriorly. Now, you don't have that with this technology. So what you have to bear in mind is that you just keep pulling the catheter back and marking it with the AutoTags. And then if it flicks, then you know that you've come back too far. So I find that quite useful, because what you're trying to achieve is that for this angle to reach 90 degrees, so once it reaches 90 degrees, you know that you're pointing anteriorly towards the appendage. And obviously, if you pull back any more, it will flick into the appendage like that. And once you have delivered your lesion set, you want to see whether or not you've got any gaps. And this is where arrhythmia really comes into its own, because obviously arrhythmia, the mapping is second to none. And it requires very limited mapping with the Orion catheter to highlight where the gaps are. In this particular case, the gaps were on the posterior carina, which again, not surprising, because remember, this is where the esophagus was, so the quality of the lesions was less good because I didn't burn for too long. And so the impedance drops were less as well. So we had a gap here quite clearly, and you can see sort of closely split potentials here. And it took just a single RF application here to eradicate this connection. And then finally, you want to create a voltage map to validate pulmonary vein isolation, which is what we did here. You can see that all the veins are well and truly isolated. And you can create the voltage map to validate posterior wall isolation as well, which is what we did. So you can see there's a roof line here, floor line here, and this is all single pass. So just one pass across the roof and the floor, we had complete silence on the posterior wall, as confirmed with the Orion arrhythmia mapping. So to summarize, what are my thoughts about this catheter? So first of all, I believe that if you use conventional force sensing, contact force sensing catheters conventionally, you will be almost certainly over-ablating, because you will be targeting ablation index or LSI targets. And also, it'll lead to a very simplistic one-size-fits-all strategy. You're not taking into equation the effect you're having on the tissue, which can be very variable from person to person, but also within the same patient from one lesion to the other. So if you're just using the same AI target of 550 everywhere, because those targets have been established, a lot of the work happened in our lab, actually in Liverpool, you want to minimize acute and late reconnection. So by its very nature, you will be over-ablating. Now, if you start using the impedance feedback, so especially local impedance feedback, as Directsense allows you to do, then you can create truly individualized lesions. So from patient to patient, but also individualized lesions within the patient. And you can ensure that every RF application counts. You have no unnecessary or very little unnecessary or extra RF energy application. Now, I would like to point out that the way this catheter is structured, the distal electrode is quite large. And also, the gap between the distance between the distal electrode and R1 is also longer than in most other catheters. So I found it quite difficult to be able to interpret the local M1, M2 bipolar signals. So I would say that the catheter is great in terms of what it allows you to do and deliver RF ablation successfully. But in terms of its diagnostic capabilities, obviously, because it doesn't have the MiFi electrodes and the distal electrode is much larger than, say, the Smart Touch catheter, you've got to be a bit careful in interpreting the M1, M2 signals. Also, I think for people who are used to using contact force sensing catheters, the learning curve should be very short. And once you use a stable sheet, as we do in our lab, any differences in catheter handling across platforms, say between Smart Touch and between the OI catheter, they're minimized anyway, because essentially what you're doing is handling the sheath. The catheter is just merely a conduit for you to deliver RF energy to the tissue. And also, as with anything, the more you do, the more confident you will get with the technology, and more your efficiencies will increase. Now, for example, with Carto, we started using Carto a few years ago. We used to use, every case used to take 4 hours, and now it takes less than half the time. And similarly, I've done this in half a dozen cases, and already I'm seeing that the case procedure duration is decreasing. So I think this is a great technology. It has really enhanced my ablation practice, at least, and I hope it will enhance yours as well. For the first time, you have in the one single catheter the ability to not only monitor your contact force, but also to assess the impact of your ablation on the tissue. And that really brings the EP back into EP for me. It gives me a very good idea of exactly what's happening. And of course, that's what got me into EP in the first place. Well, I'll end here. Thanks very much for listening. I hope you find this useful. And obviously, it's difficult to, on this platform, to be able to answer questions, unlike what we could do in a face-to-face meeting. But email me with your queries or tweet if you have any questions, and I will try my best to answer. All the best, and I hope you enjoy using this catheter.